Hello everyone. So in this session, we will look at an important subset of the set of arithmetical functions. In fact, this subset forms a subgroup of the group which we were considering of arithmetical function, that is the set of arithmetical functions with non-zero value at 1 with convolution as the operation. This will form a subgroup of that. So that is the multiplicative function. So what is a multiplicative function? It is an arithmetical function that is not identically zero and satisfies the property that if m and n are natural numbers which are relatively prime, then f of mn is f of m into f of n. We also define a completely multiplicative function, that is a function which is f of m, which satisfies the property that f of mn is equal to f of m into f of n for any mn n in n. Okay, you can see here that a function that is completely multiplicative will also be multiplicative by the definition itself. We will prove or we will find a function which is multiplicative but not completely multiplicative. It is quite easy to observe even at this stage. Okay, so first we'll prove one small theorem, that is, if f is a multiplicative function, then f of 1 has to be 1. Now notice here that f of 1, or we know that there is some, so there exists some n naught in n such that f of n naught is non-zero. Now notice that the GCD of n naught and 1, since the GCD of any natural number with 1 is 1 itself, which means that since f is multiplicative, this tells me that f of n naught, which is the same as f of n naught times 1, is equal to f of n naught times f of 1. But as f of n naught is non-zero, we could cancel it on both sides to give us f of 1 is equal to 1. So if f is a multiplicative function, then f of 1 has to be 1. Okay, so let us look at some examples of multiplicative and completely multiplicative functions. So this is the first one here. It's a very natural function. If we have any alpha in C, we can define f alpha of n to be n raised to alpha. This function here is completely multiplicative. You can very easily see that f of n times m is nm raised to alpha, but we know that this is n raised to alpha times m raised to alpha, which is f of n times f of n. So therefore this function is completely multiplicative. Next, we have also shown that phi of mn is equal to phi of m times phi of n when n and m are relatively prime, when the GCD of m and n is 1. So we have already proved this. This tells us that phi is a multiplicative function. But the question is it a completely multiplicative function? You can very easily observe that phi is not completely multiplicative. For that, you just consider phi of 4, that is 2 square. So phi of 4 we know is, so the numbers which are relatively prime to 4 is 1 and 3. So this will be 2. and phi of 2 into 2, phi of 2 into phi of 2, this will be, since phi of 2 is 1, this will be 1 into 1, which is 1. You can see that phi of 4 is not equal to phi of 2 into phi of 2. Hence it is not completely multiplicative, but it is multiplicative. What about the identity function? Okay, the identity function is also completely multiplicative. Okay, that is, suppose you start with any n and m in. So the identity function takes the value 1 at 1 and 0 everywhere else. Okay, so suppose you have n and m in M. There are two possibilities. One is either n or m is 1. So suppose n is equal to 1. In this case, I of n times m will be the same as I of m. But we know that I of n is 1 itself. So therefore this is the same as I of n times I of m. So you can see that I of nm is I of n times I of m. Now, so this happens if either n or m is 1. We have shown that I of nm is I of n into I of m. What happens if both of them are greater than 1? So n is greater than 1 and m is greater than 1. So in this case, you see that I of, so if n and m are greater than 1, n times m will also be greater than 1. So therefore, I of nm will be 0, which is 0 times 0. But I of n will also be 0 and I of m will also be 0. So this will be I of n times I of m. So this proves that the identity function is also completely multiplicative and hence also multiplicative. Okay. Next, you can also observe that if f and g are multiplicative, then f into g is multiplicative. And if f and g are completely multiplicative, then f into g will also be completely multiplicative. The proof of this fact is quite easy, so I will leave it out for you. Okay, now let us show that the function mu is, that is the Mobius function, is multiplicative but not completely multiplicative. So how do I show that it is multiplicative? Notice that the values of mu depend on the prime factorization of n. So if the prime factorization is just a product of primes with no power greater than 2, that is, if n is a square free number with k primes, then f of n will be minus 1 raised to the number of primes, and otherwise it is 0. So that is how you take your cases. So suppose, so take some n and m in n such that the GCD of n and m is 1. So suppose both n and m, so the case when either n or m is 1 is very simple. Let me just go with that first. So suppose n is equal to 1. In this case, notice that mu of nm will be mu of m, but we know that mu of n is 1, so that again will give us mu of n times mu of m. So this happens if n is 1. So we can now assume that n and m is, n is greater than 1 and m is greater than 1. Now in this, let us see two cases. Suppose n is not square free. So suppose n is not square free. So if n is not square free, this will mean that n times m is also not square free. In fact, it will have the same square divisor as n is not square free. Which means that mu of n times m is 0. Also look at mu of n into mu of n m. This will also be 0 because mu of n will be 0. So the last case which we need to consider is both n and m are square free. So suppose n is equal to some p1 raised to a1, p2 raised to a2, sorry, they are square free. So p1 times p2 up to pk, and suppose m is some different primes from this because they are relatively prime. So the n and m have distinct prime divisors. So suppose say q1, q2 up to say qs. In this case, the prime factorization of n times n will be p1, p2 up to pk into q1, q2 up to qs. This will be the prime factorization. This will be all distinct primes also. So therefore, mu of n will be minus 1 raised to k and mu of m will be minus 1 raised to s, which means that mu of n times mu of m will be minus 1 raised to k plus s. But this is mu of n. So this proves that the Mobius function is multiplicative. Now, how do you observe that it is not completely multiplicative? To observe that it is not completely multiplicative, you need to give some n and m such that mu of nm is not equal to mu of n into mu of m. So let us go with the same example that we saw earlier with the same method. So what is mu of 4? Mu of 4, since 4 is not square free, will be 0. But mu of 2 is 1 or minus 1. So therefore, mu of 2 times mu of 2 will be 1. And we know that 1 is not equal to 0, which is mu of 4. So therefore, mu of 4 is not equal to mu of 2 into mu of 2, and hence mu is not completely multiplicative. Okay, so let us prove one equivalent fact or equivalent statement to the definition of multiplicative functions. So if we have an arithmetical function which is 1 at 1, which takes the value 1 at 1, that is f of 1 is equal to 1, and suppose then we will show that f is multiplicative if and only if given any distinct primes p1, p2, pr and any natural numbers a1, a2, ar, f of p1 raised to a1, p2 raised to a2 up to pr raised to ar is f of p1 raised to a1 into up to f of pr raised to ar. This is what we will prove. The converse side of this statement is very easy. In fact, both the proofs are very easy. So let us prove the converse first. So converse. So suppose this condition holds, that is for any distinct primes p1, p2, pr and any a1, a2, ar in n, suppose this condition holds. I want to show that f is multiplicative. So how do I do this? Start with any n and m. So suppose we have some m and n in the set of natural numbers. Again, here we have two possibilities, either m is 1 or n is 1, or both of them are strictly greater than 1. So suppose one of them is 1. Say suppose m is 1. In this case, so we are using a similar technique very often. F of m times n will be f of n itself. But we know that f of 1 is 1, that is given to us. So this will be f of m, because f of m is 1, times f of n. So you can see that f of mn is equal to f of m times f of n. Now we can assume that both m and n are greater than 1. So m is greater than 1 and n is greater than 1. Let the prime factorization of m be p1 raised to a1, p2 raised to a2, up to pr raised to ar. And suppose the prime factorization of n is q1 raised to b1, q2 raised to b2, up to qs raised to bs. Now here, since m and n are relatively prime, no pi will be equal to any of the qj's. So therefore, the prime factorization of m times n will be p1 raised to a1, p2 raised to a2, up to pr raised to ar, where all of these are distinct primes. Very important to observe that all of these are distinct primes. So therefore, what will be f of mn? So f of mn we are given is f of p1 raised to a1 into f of p2 raised to a2 up to f of pr raised to ar into f of q1 raised to b1 up to f of qs raised to bs. Now this first portion will be f of m, and this part will be f of n. So this is f of m times f of n, which proves that so this proves that f is a multiplicative function. Now let us assume that f is multiplicative and prove this statement. So this portion we will do using induction. We'll use induction on R. So to prove by induction, first let us prove when R is equal to 1. When R is equal to 1, there is in fact nothing to prove, because here you have p1 raised to a1 is anyway f of, the right hand side is f of p1 raised to a1 and the left hand side is also f of p1 raised to a1. So there is nothing to prove in the case when R is equal to 1. Now we assume that this statement holds. So we assume that this statement holds for any k primes, or let's say for any r primes, and any r positive integers a1, a2 up to ar, f of p1 raised to a1 up to f of pr raised to ar is equal to f of p1 raised to a1 up to f of pr raised to 1. So we have assumed this. We now need to prove it for the r plus 1 stage. So for that, we start with any r plus 1 prime. So let p1 up to pr plus 1 be r plus 1 primes, and say we have a1 up to ar plus 1 be r plus 1 positive integers. Now what is f of p1 raised to a1 up to f of pr plus 1 raised to r plus 1, ar plus 1. Notice that these two integers here are relatively prime because pr plus 1 is different from all the previous primes. Therefore, these two integers are relatively prime. So this, since f is multiplicative, will be f of p1 raised to a1 up to pr raised to ar into f of pr plus 1 raised to ar plus 1. But by the induction hypothesis, this is equal to f of p1 raised to a1 up to f of pr raised to ar. So this is f of p1 raised to a1 up to f of pr raised to ar times f of pr plus 1 raised to ar plus 1. And this proves our claim. So f is multiplicative if and only for any distinct primes p1, p2 up to pr and a1, a2 up to ar. This condition holds, and we need to also have that f of 1 is 1. So this is another way of checking whether a function is multiplicative. Okay, now if we are given a multiplicative function, so if f is a multiplicative function, then we can check whether it is completely multiplicative. This is something which we will use quite often. So then f is completely multiplicative if and only if for any prime p and for any a in n, f of p raised to a is equal to f of p the whole raised to a. Okay, that means I can take out that a from here. So this is again a very simple fact. So let us first prove the direct part of the statement, that is, assume that f is completely multiplicative. So suppose f is completely multiplicative and p is a prime, and say a is some natural number. So I want to prove that f of p raised to a is equal to f of p the whole raised to a. But since f is, this in fact can be done by induction. Say we do induction on a itself. So if a is 1, then there is nothing to prove, because f of the left you will get f of p raised to 1, which is f of p, and here you will get f of p the whole raised to 1, which is again f of p. So there is nothing to prove when a is 1. So we can assume the result for a and prove for a plus 1. But f of p raised to a plus 1, this will be, So this will be f of p raised to a into f of p, but we have already proved that f of p, we have assumed that in the induction hypothesis we have assumed that f of p raised to a, so we need to make that assumption. So assume that f of p raised to a is equal to f of p the whole raised to a. So this will be f of p the whole raised to a times f of p, which is f of p the whole raised to a plus 1. So therefore we have proved this statement. Now let us assume that f is multiplicative and satisfies this condition. We now need to prove that f is completely multiplicative. So to prove that f is completely multiplicative, we start with some n and m in, or m and n in the set of natural numbers. We need to prove that f of mn is equal to f of m into f of n. So the first case is the same as before. Suppose m is equal to 1. If m is equal to 1, you'll see that this case will follow the same way all the time. This is f of mn is equal to, now since since m is 1, this is the same as f of n. But since f is a multiplicative function, we know that f of 1 is 1. So therefore this will give me f of m times f of n. So in case either m is 1 or n is 1, we see that f of mn is equal to f of m times f of n. Next, we assume that both m and n are greater than 1. The reason why we do this is so that we can use the prime factorization. So suppose this is the next case. M is greater than 1 and n is greater than 1. So let us look at the prime factorization of m and n. So the prime factorization of m is p1 raised to a1. Let us suppose that the prime factor is p1 raised to a1 up to pr raised to ar, and say the prime factorization of n is, we now need to be a little careful because we don't know that m and n are relatively prime, hence they might have some similar prime. So therefore we can take p1 raised to a1, pr raised to ar, and n take as p1 raised to a1 up p1 raised to b1 up to pr raised to br. Okay, but here we will need to allow that the ai's and bi's are either positive integers or 0. Okay, you can always do this. Let me give you an example. So here if you have 4, if m is 4, then this is 2 square and 6 is 2 times 3. So here you can write this as 2 raised to 2 into 3 raised to 0, and here you can write this as 2 raised to 1 into 3 raised to 1. So you can see I am using the same primes just by putting zeros. Just if I allow the powers to be zeros, I can do this. So now what is f of mn? F of mn is nothing but f of p1 raised to a1 plus 1, a1 plus b1 into f of into p2 raised to a2 plus b2 up to pr raised to ar plus br. But this here will be, because f is a multiplicative function, this will be f of p1 raised to a1 plus b1 into f of p2 raised to a2 plus b2 into up to f of pr raised to ar plus br. Okay, but now we are given that f of p raised to a is the same as f of p the whole raised to a. So this will be f of p1 the whole raised to a1 plus b1 into f of p2 the whole raised to a2 plus b2 up to f of pr the whole raised to ar plus br. Okay, this we can see is the same as f of p1 the whole raised to a1 up to f of pr the whole raised to ar into f of p2 the whole raised to b1 up to f of pr whole raised to br. But this here again as again using the same property again, the same property that we have used from this stage to this stage. This will be f of p1 raised to a1 up to f of pr raised to ar into f of p2 raised, which is p1, I'm sorry, this is p1 raised to b1 up to f of pr raised to pr. But this portion here is f of m. Okay, this will be f of m, and this section here is f of n. So how is this f of m and f of n? Because using the fact that f is multiplicative, this will be f of p1 raised to a1 up to pr raised to ar into f of p1 raised to b1 up to f of pr raised to ar, pr raised to br. And this here you can see is m and this is n, so you get f of m times f of n. So this proves our result. Okay, let's prove a few exercises of basic number theory. So we will show that if the GCD of m and n is 1 and c is a divisor of mn, then there is some a and b in n such that a divides m and b divides n and c is equal to ab. So that is the way the divisors of m and n will look like. They're going to look like some ab, where a divides m and b divides m. And we will also prove the converse of this theorem. So first assume that the GCD of m and n is 1 and c divides mn. We need to show that there is some a and b. So we need to catch hold of what that a and b is. Yes, so this is quite clear when m is equal to 1. So if m is equal to 1, then c will be a divisor of m, because c divides mn. Sorry, c divides mn. So this means that c will be a divisor of n. Okay, so c is a divisor of n. So I can choose a to be 1 and b to be c itself. and therefore you will have C is equal to A times B, and you'll have and you also know that A divides M and B divides M, because B is C. Okay, so this case is quite obvious if either M is 1 or N is 1. So let us assume that both M and N are greater than 1. So suppose M and N are greater than 1. In that case, so M is greater than 1 and N is greater than 1. In this case, you can write down the prime factorizations of M and N. So you can write M as P1 raised to A1 up to PR raised to AR, and you can write N as Q1 raised to B1 up to Qs raised to Bs. Okay, and since M and N are relatively prime, these primes, these Pi's are not equal to any of the Qj's. So the Pi's are never equal to the Qj's. Okay, so since the Pi's are never equal to the Qj's. Now we know that C divides Mn. Okay, but divisors of an Mn will just be P1 raised to A1, PR raised to AR, Q1 raised to B1, Qs raised to Bs. So the divisors of Mn, so this means that C will be something of the form P1 raised to say T1, P2 raised to T2 up to PR raised to TR into Q1 raised to say U1 up to Qs raised to Us. Okay, so this is what C will be. So what could I take A and B as? So here you choose A to be P1 raised to T1 up to PR raised to TR, and you choose B to be Q1 raised to U1 up to Qs raised to Us. Okay, now notice that A into B is C. Okay, but we still need to prove other things. That is, we need to prove that A divides M and B divides N. But here you notice that since C is a divisor of Mn, these Ti's should lie between, so the Ti's should lie between 0 and Ai's, while the Ui's or the Uj's should lie between 0 and the Bi's, the Bj's. So therefore, A will divide M and B will divide N. So we have proved the direct side of the exercise. Now we need to prove the reverse direction. That is, if there exists some A and B such that A divides M and B divides N and C is equal to AB, then we need to show that C divides M times N. So this is again not a very difficult statement. Now first, so we can prove this. We can also prove this using the prime factorization, but since M and N are relatively prime, let's use this fact. Since M and N are relatively prime, so the converse. As M and N are relatively prime, there will be some X and Y in Z such that Mx plus Ny is equal to 1. Okay, notice that we need to show that C divides M times N. Okay, so the natural way of doing it is to get M times M on this side. So So we multiply throughout by m times n. That will give us m times n times x plus m times n times y equals mn. Now, okay, so now notice that A divides m and B divides n, which means that A times B will divide this part. Also, A divides m, B divides n, so AB will divide this part, and therefore AB is going to divide mn. So therefore this tells me that AB divides mn. So this proves our theorem or our exercise. Okay, so there is a reason why we are proving this exercise. You will see that in the next theorem. So let us prove that if m and n are natural numbers which are relatively prime, then these two sets have the same number of elements in it. Okay, they have the same number of elements in it. So to prove that these two sets have the same number of elements in it, we construct a bijection. So define a function f from C in n such that C divides mn to the set a comma b in n cross n such that a divides m and b divides n. Okay, the natural way to define this would be f of a times b. Okay, because this is a divisor of mn, so it is going to look like some ab where a divides m and b divides n. Okay, so we'll take this to a comma b. So that is where a divides m and b divides n. The first thing which we need to see here is whether this function is well defined. That is, suppose, so let us show that this function is well defined. So suppose a1 times b1 is equal to a2 times b2, where the ai's divide m and the bi's divide n. I is either 1 or 2. So what will this mean? So this means that a1 divides a2 times b2. Okay, now notice here that a1 is a divisor of m and b2 is a divisor of n. So a1 divides m and b2 divides n, which will mean that since m and n are relatively prime, the only common divisor of m and n is 1 itself. Okay, so or another way of doing this is, since m and n are relatively prime, you can have some x and y such that mx plus ny is 1. So therefore this tells me that oh sorry, this cannot be done. Okay, so I want to say that the GCD of A1 and B2 is 1. So suppose D divides A1, D is a divisor such that D divides A1 and D divides B2. What does this mean? This will mean that D divides M and D divides N. But the only common divisor of M and N is 1. So this means that D is equal to 1. Hence, the only common divisor of A1 and B2 is 1. That means that A1 and B2 are relatively prime. Or in other words, this tells us that A1 divides A2. Similarly, you can show that A2 divides A1. And therefore, this will tell us that A1 is equal to A2. And hence, you can also show that, or by cancelling out A1 and A2 on both sides, you get B1 is equal to B2. So, we have shown that this is a well-defined function, okay, because then the images will be the same. Okay, so now let us show that if f and g are arithmetical functions such that g is multiplicative and f convolution g is multiplicative, then f is a multiplicative function. Okay, so to prove this, let us go by contradiction. So suppose f is not multiplicative. Now f is not multiplicative could mean two things: either f is identically 0, or there is some m and n such that f which are relatively prime, such that f of m times n is not equal to f of m times f of n. Now f cannot be identically 0 because that will contradict the fact that h is multiplicative. So therefore, if f is not multiplicative, there has to be some mn such that f of mn is not equal to f of m times f of n. So let us assume that f is not multiplicative. If f is not multiplicative, it means that there exists m0 and n0 in the set of positive integers such that the GCD of m0 and n0 is 1 and f of m0 times n0 is not equal to f of m0 times f of n0. Okay, so now let us look at this set S. So we consider this set S to be the set of all mn such that m and n are positive integers. The GCD of mn is 1 is equal to 1 and f of mn is not equal to f of m times f of n. Notice here that m0 times n0 is in S, which means that S is non-empty. Okay, so therefore by the well ordering principle, we know that S has a least element. So S has a least element. Let us call the least element as m1 times n1. So what is the meaning that this is the least element? It means that the GCD of m1 and n1 is 1 and f of m1 times n1 is not equal to f of m1 times f of n1. It also means that if A and B are some two natural numbers such that AB is strictly less than m1 times n1, and suppose the GCD of a and b is 1, then since this is the least element, it means that f of ab will be the same as f of a times f of b. So this is the meaning that m1 times n1 is the least element of S. Now, is it possible that m1 times n1 is 1? So what would happen if m1 times n1 is 1? If m1 times n1 is 1, it means that m1 and n1 are both 1. Okay, but what is f of 1? So let us look at what is f of 1. So we know that f convolution g at 1, okay, this will be f of 1 times g of 1. But we are given that f convolution g is multiplicative, which would imply that f convolution g at 1 is 1, and g is also multiplicative, which means that g of 1 is 1. So this will tell us that f of 1 is equal to 1. And since f of 1 is 1, we see that this equation is not satisfied. That is, if I put m1 equals 1 and n1 equals 1, you will get the LHS to be equal to the RHS. Therefore, this means that m1 times n1 cannot be 1. You can't have this choice. Okay, so this means that m1 times n1 should be a number bigger than 1. Now, let us look at what is h of m1 times n1. So what is this? By definition, this is summation d divides m1 times n1 f of d times g of m1 n1 upon d. Let us take out the m1 n1 term from here. Okay, so this will give us summation d divides m1 n1 d strictly less than m1 n1 f of d g of m1 n1 upon d plus f of m1 n1. Okay, so this is what we get. Now we know that all divisors of m1 n1 are of the form ab, so that a divides m1 and b divides n1. So let's look at ab. So a divides m1. This is the form a divides m1, b divides n1, and we have ab is strictly less than m1 times n1. This will be f of ab g of m1 n1 upon ab plus f of m1 n1. this will be equal to summation a divides m1, b divides n1, ab strictly less than, this is strictly less than m1 times n1. Now, since AB is strictly less than m1 n1 and AB are divisors of m1 and n1 respectively, we also know that m1 and n1 are relatively prime, which means that AB is relatively prime. And therefore, since m1 and n1 is the least element such that that equation is not satisfied, therefore we can split this up into f of a times f of b. Also, since g is multiplicative, this can be written as g of m1 upon a into g of n1 upon b, plus here this is f of m1 n1. Now let us add and subtract the term f of m1 into f of n1 to this. Okay, so if we add the term f of n1 in f of m1 into f of n1 to this, what do we get? We will essentially get the sum a divides m1, b divides n1, f of a, f of b. So we are not putting the condition that ab is strictly less than m1, because that adding f of m1 times f of n1 to this, you will get, when you can see here, when a is m1 and b is n1, you get g is 1. Okay, g of you get g of 1 is 1, g of 1 is 1, so that will not contribute anything. G of n1 upon b plus f of, and we need to subtract f of m1 times f of n1 from this. You can more or less identify what we are doing here. So what will this be? You can combine this term with the first term and this term with the second term. You will see that this is the same as summation a divides m1 f of a g of m1 upon a the whole into summation b divides n1 f of b g of n1 upon b plus f of m1 times n1 minus f of m1 times f of n1. Okay, this will be equal to, here you can see this, okay, is h of m1, and here this is h of n1. Okay, so this is h of m1 and h of n1. So this is h of m1 times h of n1 plus, I think maybe we should use the next board. Okay, so this will give us h of m1 times h of n1 plus f of m1 n1 minus f of m1 times f of n1. Now notice here that this value here is non-zero, because we know that f of m1 times n1 is not equal to f of m1 into f of n1, which means that this is not equal to h of m1 into h of n1. And this is a contradiction because h is given to be a multiplicative function, and we started with h of m1 into n1. So this is a contradiction, which means that f is a multiplicative function. F is multiplicative. Okay, And this gives us a corollary which states that if g is a multiplicative function, then g inverse is also multiplicative. So how do we prove this? A very simple proof to this is, you know that g convolution with g inverse is the identity function. Okay, now identity function is multiplicative. Also g is multiplicative. Okay, which means that g inverse is multiplicative, and that's the proof. So this tells us that the set of multiplicative functions with convolution is closed under taking convolutions, and it is also closed under taking inverses. Okay, so this proves that the set of multiplicative functions is a group by itself with convolution. That means a subgroup of the group of arithmetical functions with non-zero value at 1. Okay, so this gives us that proof. So now let us see some more theorems of multiplicative functions. So if f is a multiplicative function, we would like to know if it is completely multiplicative. So there is an equivalent statement here that says that f is completely multiplicative if and only if for any n, f inverse of n is mu of n times fn. So suppose f is completely multiplicative. Okay, so suppose f is completely multiplicative, we want to show that f inverse of n is mu of n times f. There is only one way of doing this, is we take the convolution of this function with f. So f is completely multiplicative. Let's look at what is f convolution with mu times f. So this at n, what does this give us? This is summation d divides n f of d times, so this will be mu of n by d into f of n by d. Now since f is completely multiplicative, this here will give me f of n. So this will give me summation d divides n f of n times mu of n by d, which is basically f of n outside into summation d divides n mu of n by d. But this, as d varies over n over all the divisors of n by d also varies over all the divisors, so this is just mu of d. This here we know is in. Okay, this is I of n. This is f of n times I of n. But I of n is 0 when n takes any value greater than 1, and it is 1 when n is 1, and also f is 1 when n is 1. So this tells me that this here will be I of n, and hence this tells me that the inverse of f will be mu f. So this proves one side of the statement. Conversely, suppose f inverse is mu times f. Now we know that f is a multiplicative function, so you need to keep that in mind. So f inverse is mu times f. So what we need to show is, we need to take any prime and any a in the set of natural numbers, and we need to prove that f of p raised to a is the same as, we need to show that f of p raised to a is the same as f of p the whole raised to a. So how would I go about with that? So it seems natural to use induction here. So for a equals 1, there's absolutely nothing to prove. So we assume the case for a. So assume that f of p raised to a is equal to f of p the whole raised to a. And let us prove this for f of p raised to a plus 1. So let's look at what is so we know that f inverse is mu times f, which means that f times mu times f will be I, which tells me that f convolution mu of f, mu times f at p of p raised to a plus 1, this is 0, okay, because this is not equal to 1, so that means this is 0, which would mean that, let's look at what this breaks down to. So this is summation d divides p raised to a plus 1, which is essentially just I going from 1 to a plus 1 f of or 0 p raised to I mu times mu of p raised to a plus I minus 1 minus a plus 1 minus I, a plus 1 minus I into f of p raised to a plus 1 minus I. This is what you will get. Okay, so this would be 0. Notice here that this mu will be 0 as long as I is not equal to a plus 1 and I is not equal to a. Only in these two cases it will be non-zero. You can see that because you will get, when I is equal to a plus 1, you'll get mu of 1, which is 1, and when I is equal to a, you will get p, which is minus 1. In every other case, you're going to get 0. So let's see what this works out to be. So you're only getting the terms when I is equal to a, so that will be f of p raised to a into f of p plus f of p raised to a plus 1. Okay, now you will get a minus sign here because mu is minus 1 into f of 1, because this is minus a plus 1, so this is 1. This is equal to 0, which means that f of p raised to a plus 1 equals f of p raised to a times f of p. But this here you can see f of p raised to a is the same as f of p the whole raised to a times f of p. This is f of p the whole raised to a plus 1. This proves our result. Therefore, we have shown that if f is multiplicative, then it is completely multiplicative if and only if this is the inverse of f. Okay, so next let us look at this sum here. It looks interesting. Let us try to evaluate this sum. So this sum can be evaluated as long as you know the prime factorization of n. In fact, as long as you know just the prime factors of n, okay, if you can catch hold of the prime factors of n, you can evaluate this sum. And this seems quite natural. So the natural way of doing this is you take h to be the arithmetical function mu of t, f of t. Now notice here that mu is multiplicative, f is multiplicative, therefore mu times f is also going to be multiplicative. Okay, if f and g are multiplicative functions, then f times g is also multiplicative. You can very fast see that proof. Even though I have not proved it, it is very easy. So mu times f is multiplicative. The moment mu times f is multiplicative, this sum here h is going to be a multiplicative function. Okay, so h is going to be a multiplicative function. So let's use that. So suppose the prime factorization of n is p1 raised to a1 up to pr raised to ar. So since h is multiplicative, h of n will be h of, let me write it like this, it will be the product, okay, it will be the product I going from 1 to r, h of pi raised to ai. So I only need to compute what is h of pi raised to ai. What is h of pi raised to ai? Now this has worked out to be quite simple. So h of pi raised to ai, okay, this will be summation. So it's summing over the divisors of pi raised to ai, which is going to be, say, t going from 0 to ai, mu of p raised to t into f of p raised to t. Now this value here will be 0 except for the first term and the last term, first term and the second term, that is when t is 0 and t is 1. When t is 0 you'll get 1, and when t is 1 you'll get minus 1. So this will become, when t is 0, f of 1 will be 1 because f is a multiplicative function. So this will give me 1 minus, when t is 1, you're going to get minus 1 here, and here you will get f of p. Okay, so you substitute that in this equation here, you will get product I going from 1 to r, 1 minus f of p, which is exactly what this is. Okay, these are, the notation here is basically prime divisors of n when I write p divides n. Okay, so this proves this theorem. Okay, now let us show that the inverse of phi of n is product p divides n 1 minus p. We have proved earlier that given any n, it is equal to summation d divides n phi of d. Okay, this is what we have proved. So what does this mean? This means that n, capital N, that is n of n equals n, this is a multiplicative function, if you can see. So this will be equal to phi times phi convolution with u, where u of n is 1. And this means that if you take the inverse of u, you will get phi is equal to n convolution with u inverse. Okay, this is n convolution with u inverse, which means that phi inverse will be u convolution with n inverse. So I need to know what is n inverse. Now, what is n inverse? N is in fact a completely multiplicative function. So since it is completely multiplicative, we have proved just now that the inverse of n will be mu times n. So this is mu times n. So once we have this, it is quite easy to observe what is the inverse of 5. Okay, so now you can see here phi inverse of any n will be summation d divides n. U of t, we could look at this as also mu n times u, which will make it a little easier. So this will be mu times d into n times d, okay, into u of n by d, but u of n by d is always 1. And here we can see that this is what we have proved earlier here. So this will be equal to 1 minus, so the product over the prime divisors of n, 1 minus n of p, which is p itself. Okay, this is product p divides n, 1 minus p. So this proves this exercise. Okay, with this we will end this session and I will see you in the next session. Thank you.